Hi, I'm Dr. Gareth Moore from RP Photonics, and welcome to this RP Fiber Power tutorial series. Today I'm going to show you how simple to use, yet powerful, our fiber simulation software is. Let's dive right in with a case study which you can find on our website. In this video, our goal is to design a ytterbium doped fiber laser emitting at 975 nanometers. This laser wavelength is quite interesting. While we do have an emission cross-section maximum here, we also have similarly strong reabsorption. This means we only get positive gain if the ytterbium doping density is greater than 50%. This has interesting implications and turns out to be rather difficult to do, especially for designs using double-clad fibers. Let's see how it's done using RP Fiber Power. For this simulation, we use the power form titled Continuous Wave Fiber Laser and Amplifiers. Our first attempt at creating a ytterbium doped fiber laser at 975 nanometers will be done using a core doped single mode fiber. To do this, we select our fiber from the list of commercially available options. We set the length to 3 meters and the laser wavelength to 975 nanometers. The end reflectances are set to 10% for the output coupler and 99% for the backside. Next, we activate one pump with a wavelength of 940 nanometers in the forward direction with a power of 250 milliwatts. We also want the simulation to take account for amplified spontaneous emission, in short ASE, as this often plays a significant role in fiber laser design. We also need to set the ASE wavelength range to ensure it covers a significantly wide spectral range. Finally, we choose some output diagrams to visualize our results. First, we'll look at how the powers of the signal, pump, and ASE evolve along the fiber, as well as the ASE spectra, with a special interest in the gain spectrum. Let's inspect the output of the laser. We have achieved an output power of 166 milliwatts, with some residual pump power and very little ASE. So this design already works quite well. Let's take a closer look inside to understand how this happens. The powers versus position diagram shows the pump being absorbed along with the forward and backward signals in the resonator. We also see that the excitation, indicated in grey, stays above 50% for the entire length. Additionally, there is only a minimal amount of ASE. Examining the ASE spectra, we can see that although the gain around 1030 nanometers is slightly higher than the laser gain at 975, it is not enough to cause excessive ASE output. Since the absorption of the pump light is quite incomplete, it seems logical that increasing the length of the fiber would produce more laser power. Let's use one of our parameter variation diagrams to test this out. We vary the length of stage 0, meaning the laser, from 0.5 meter to 4.5 meters. Interestingly, we see that the output power drops steeply after 3.5 meters. To understand this better, we set the laser stage to 4.5 meters and examine the outputs. In the powers versus position diagram, we observe more pump absorption. But after 3 meters, this is not enough to maintain more than 50% excitation. This results in a strong signal reabsorption, causing ASE to become dominant and resulting in less signal power than before. However, at 3 meters, we still have a functioning laser system. To achieve significantly higher powers, we now try using a double-clad fiber. We select a double-clad fiber and set the pump wavelength to 920 nanometers, where absorption is even stronger, and increase the pump power to 50 watts. We run the simulation and quickly see that this completely fails, with incomplete pump absorption and a lot of ASE. Our first attempt to address this is to suppress the ASE with a backside mirror that only reflects at 975 nanometers. This has a significant effect, resulting in both forward and backward ASE, but we still cannot reach the laser threshold. Finally, we increase the length of the fiber in hopes of achieving more complete absorption. While we do get more pump absorption, we simply produce more ASE. To further understand this, we examine the ASE and gain spectra. This shows that we only have some positive gain from 1030 nanometers, and this is where we see the ASE. All this indicates that we would not be able to realize a 975 nanometer laser with this type of double-clad fiber. To get sufficient pump absorption, we need a high concentration of ytterbium, but as we ramp up the excitation, we first get a strong positive gain at 1030 nanometers, resulting in strong ASE in that spectral region. This limits the achievable excitation, and as a result of that, we cannot achieve the positive gain we need at 975 nanometers. One way to fix that serious problem is to modify the distribution of ytterbium ions in the core. We place the ytterbium dopant only in a ring, where the signal intensity is smaller, and not in the center. As a result, we can have a higher ytterbium excitation, which favors gain at 975 nanometers over that at longer wavelengths. In the form, we activate the Show Override section, where we can customize the specifications of the standard fiber in various ways. We define the new doping profile with ytterbium ions only at the radius of 4.5 to 5 microns. Double the doping density and increase the simulated core radius so that the ring falls within the core. Next, we extend the fiber length even further to 20 meters to maximize pump absorption and ensure that we increase the radial numerical steps to accurately capture the ring structure. We see that this approach actually works, producing more than 20 watts of 975 nanometer laser light with very little ASE, even though the pump absorption efficiency is still not ideal. The laser could be optimized further. I hope you've seen today how easy it is to run through different design iterations and strategies with RP fiber power. We ran through multiple laser designs, some which failed and some which worked quite unexpectedly. But most importantly, we could figure out why. Imagine trying this through trial and error in a lab. With these simulations, we ended up not only with a good design, but a better understanding of the laser itself. To learn more about what our software can do for you, visit our website and click on the Software tab. For more case studies like these, click on the Case Studies and Tutorial button under the Encyclopedia tab. Thanks for watching, and please feel free to reach out with any questions.